You know, we're surrounded by this invisible language. It's literally what's zapping data from a server halfway across the world to your phone, letting you stream shows in crystal clear quality. So today, we're going to pull back the curtain and demystify that language, the digital signal.
And really, it all boils down to a pretty simple question, but with a seriously cool answer. How does a basic on or off, a 1 or a 0, make it all the way across the globe and turn into the movie playing on your screen? Well, that's exactly what we're going to unpack right now.
All right, let's start at the very beginning. We're talking about how we take that abstract information, those ones and zeros, and turn them into a real, physical, electrical signal that can actually go somewhere.
So at its absolute core, a digital signal is incredibly simple. Seriously, just think of it like a light switch. We can say, okay, a positive voltage means 1 and 0 voltage means 0. And by flicking that voltage switch on and off really fast, we can send a whole stream of bits down the line.
Okay, but this is where it gets really clever. How do you send data faster without actually flipping the switch any quicker? Well, check this out. The top signal has just 2 levels. On or off, right? That sends 8 bits in 1 second. But look at the bottom one. By using 4 distinct voltage levels, each level can now represent 2 bits at the same time. And just like that, boom! We've doubled our speed to 16 bits per second. We didn't make it faster, we made it smarter.
So this brings up the next logical question, right? If 4 levels gets us 2 bits at a time, what happens if we get even fancier? What if we use a signal with 8 different voltage levels? Just how much more data can we cram into every single one of those signal changes?
And the answer, believe it or not, comes from a pretty simple formula. The number of bits you can represent is just the log base 2 of L, where L is your number of levels. So for our 8 levels, the log base 2 of 8 is 3. That means each of our 8 voltage levels can now represent a unique combo of 3 bits. How cool is that?
Okay, so that's all the theory, but what does this stuff actually look like in the real world? Let's get practical and actually calculate the bit rates for some things you and I use every single day.
All right, first up, let's just talk about plain old text. Imagine you wanted to download 100 pages of text, not in a minute, but every single second. What kind of digital pipeline would you even need for that?
So let's break it down. You've got 100 pages a second. Let's assume, an average of 24 lines per page, maybe 80 characters on each line, and then 8 bits for every single character. You multiply all that together and you get a grand total of 1.636 megabits per second. Now, stop and think about that for a sec. Just for plain text, we're already talking about a connection speed that's faster than what early broadband was. That really puts our modern demand for speed into perspective, doesn't it?
Okay, let's step it up a notch. We've done text, now let's talk about voice. What does it actually take to digitize a standard phone call? The kind that uses a 4 kilohertz voice channel.
Well, the key here is a really important rule called the Nyquist theorem. It basically says you have to sample the signal at double its highest frequency to capture it properly. So we take our 4,000 samples per second, we multiply that by 2, and then we'll say each one of those samples is represented by 8 bits of data.
And that calculation lands us squarely at 64 kilobits per second. Now, this isn't just some random number. For decades, 64 kbps has been the absolute gold standard for digital voice. It's really a cornerstone of modern telecommunications.
Okay, and now for the main event, the big one. What about the high-definition video that we're all streaming constantly? What kind of bit rate are we talking about here before any of that clever compression stuff gets applied?
Yeah, brace yourself, because the numbers here get absolutely massive, and they get massive fast. A standard HD screen is 1920 by 1080 pixels. That screen is refreshing 30 times every single second, and every single pixel needs 24 bits just to represent its color.
So what's the grand total? An absolutely mind-blowing 1.5 times gigabits per second. That's 1.5 billion bits of data every single second. This right here is the perfect illustration of why video compression isn't just, a nice feature. It is the only reason streaming video is even possible for us.
So it's clear we can generate these insanely fast digital signals, but actually sending them, that's a whole other story, because now we're running smack into the hard limits of physics, and that limit has a name: bandwidth.
Now, this is a crucial concept, and it's kind of paradoxical.
A perfect digital signal, with those perfect sharp instantaneous jumps from 0 to 1, it's actually made up of an infinite number of smooth analog sine waves. We call them harmonics. And to send that perfect signal, you'd need a channel with infinite bandwidth, which, as you can probably guess, doesn't exist in the real world. And this is what happens when you try. Take a look. If you try to send that digital signal over a channel with really low bandwidth, you can only fit that first, most basic harmonic. And the result, that yellow wave, it barely looks anything like the original pink digital signal. The information is pretty much gone.
But now, check out what happens when we have a channel with more bandwidth. By adding just 2 more of those harmonics, the 3rd and the 5th, all of a sudden the resulting wave starts to look a whole lot more like that sharp square wave we started with. The takeaway is simple. More harmonics equals a more accurate signal.
And honestly, this table just sums it all up perfectly. As you go across the rows, you see it plain as day. If you want a more accurate signal by adding more harmonics, you need more bandwidth. And then if you look down the columns, you see that if you want to send data faster, if you want to crank up that bit rate, you also need more bandwidth. It is the fundamental trade-off of all digital communication.
So engineers are always up against this challenge. And to solve it, they've basically come up with 2 main strategies. We call them baseband and broadband transmission.
Okay, first up is baseband. This is the most direct, straightforward approach. Just think of the Ethernet cable that's probably plugged into your computer right now. That's a dedicated channel built specifically for digital signals. We call it a low-pass channel because its usable frequency range starts all the way down at 0 Hz. You just put the signal right on the wire and let it rip. Simple, powerful, and effective.
But what if the channel you have to use wasn't built for digital? Like, say, an old-school telephone line. That's what we call a bandpass channel. It can only carry a very specific slice or band of frequencies. So here, you got to get clever. You use a process called modulation to basically disguise your digital signal as an analog wave that fits perfectly inside that frequency band. This little trick is the magic behind stuff like DSL.
So let's just put them side by side real quick to make it super clear. Baseband, that uses a low-pass channel for a direct digital signal. The perfect example is a wired local area network. Broadband, that uses a bandpass channel and has to use a modulated analog signal. The classic example there is your DSL modem pushing data through a phone line. See, 2 totally different problems leading to 2 totally different solutions.
And all of this brings us right back to the one fundamental rule that governs absolutely everything we've talked about today. It's the inescapable law of digital communication. Speed costs bandwidth. If you want to send bits faster, you simply need a wider digital pipe to send them through, period. Which really leaves us with one last big question to think about. Our hunger for data, for faster downloads, higher res streaming, for instant communication, is just exploding. So the question for the future is this. Are our biggest breakthroughs going to come from finding even more clever ways to pack more bits into the same amount of bandwidth, or are we just stuck in a constant, never-ending race to build bigger, wider digital highways to carry it all? Something to think about. Thanks for